Okay, let's look now at the power required to maintain steady level flight. So power required. So we previously talked about the thrust required in some other videos. And now we want to talk about the power required. Okay? And the power required is very closely related to the thrust required. It's actually, so power required is simply TR V cosine of alpha t. Okay? Now, throughout this section, we're going to use the common thrust angle, small thrust angle approximation. So in other words, we're going to say that thrust angle is approximately 0. And so what this means then is that the power required is approximately equal to, power required is approximately equal to the drag times the velocity. And of course, this comes from, of course, we're in steady level flight, and if the thrust angle is 0, then the drag and the thrust have to be aligned to maintain steady flight. Okay? All right, so here's what we have. And what we want to do then is we want to find an expression for the power required as a function of some known design and aerodynamic parameters. Okay? So let's look first at V. Okay? So how do we get V? Well, recall that that CL is a function of V. Okay, so let's look at the lift coefficient. The lift coefficient in steady level flight can be written as weight divided by 1/2 rho V squared SW. Okay, so here's our V, here's our CL. Well, let's solve for V. This gives us then is V equals the square root of 2 W over SW, which we know as the wing loading, divided by rho CL. Okay? Well, great. Let's plug that back in. Now we have the velocity as a function of the lift coefficient, the weight, the wing area, free stream density. So PR equals TR times root 2W over SW rho CL. Okay? And of course, this is nearly equivalent to drag times the same thing. Okay? Again, here we've assumed that the thrust angle is very close to 0, so the cosine term is not here on the end. Okay, now let's look at thrust required. So in some other videos, we derived that the thrust required for the small thrust angle approximation is CD over CL times W, or you may know it as, not approximately equal to. I think originally we derived it as W over L over D, right? So we can see that this is the same thing. All right? We're going to stick with this expression because we know what the CD is as a function of CL. Okay, so let's look at this. So CD, let's take this whole term actually. So CD over CL times W equals CD naught over CL plus CD naught L plus CL over pi E RA. I hope you're getting familiar now with our expression for drag. Okay, so it looks like that. So if we put everything together then, we're going to put in our velocity, which we already have, and our thrust required in. I'm going to change colors so that we can kind of see a little bit better what's going on. Okay, so now we have a new expression for the power required. And it's going to look like this. CD naught over CL plus CD naught L plus CL over pi ERA times W times 2W over SW over rho CL. Okay? All right, now there's a few things we can do. One, we can take this last term here and we can divide it up. So I'm going to change colors, okay? So this last term can be written as square root 2 times W times root W over SW over rho times root 1 over CL. Okay? Now the reason we do this is because we want to simplify this, and what we want to do is factor this root 1 over CL right back in here because we have these other CLs in here. Okay? And then also this term here, this W over SW over rho, is something that shows up in our airspeeds a lot. So it showed up in our minimum drag airspeed, and so it's nice to have it there. Okay, so if we break it up this way and distribute this 1 over CL, then we get power required equals, I'm going to put the square root of 2 at the front, root 2 times CD naught over CL to the 3/2 plus CD naught L over CL to the 1/2 plus CL to the 1/2 divided by pi ERA all times square root of, times W, all times square root of W over SW over rho. Okay? Okay, so from here, let's go back and look at CL. We have an expression for CL, right? So why don't we plug that in everywhere we have CL? So if we do that and then simplify, I'm not going to go through all of the steps here again. So I encourage you to do that in your own time. But here, let me type it in. So plug in CL equals W over 1/2 rho V squared SW. Because of course we are in steady level flight. We're still looking at the power required to maintain steady level flight. So if we plug that in, then we're left with PR equals CD naught rho V squared, or V cubed, divided by 2 over W over SW plus CD naught L times V plus 2 W over SW over pi ERA rho V times W. Okay, so again, what I did is I plugged this in and then I distributed this last term. So we took this last term and threw it in. Okay, and this is what we come up with. This is our final expression for the power required. Okay, let me just make sure that's correct. Okay, it looks good. All right, so just to recap, we started with the power required and related it to the thrust required, because of course power is a force times a velocity. And this cosine of alpha t came from the fact that sometimes our thrust is offset from the velocity. But if we assume that the alpha t is close to 0, then we can say that the power required is just the thrust required times velocity, or is close to the drag required, or the drag times the velocity. Okay. So we replace the velocity with something containing the lift coefficient. We replace the thrust required with a known expression. And then we did some simplifications, plugged back in the lift coefficient, and came out with this answer. So now we have the power required as a function of velocity, and you'll notice that the lift coefficient is nowhere in here, nor is the drag coefficient, although we do have some terms that come from our drag coefficient equation. Okay, so now the way this looks is something like this. Okay, so let's take an axis here. I'm going to switch to green. And sorry, let me label the axes real quick. So if we take the power required as a function of velocity, it's going to look something like this. Oh, where am I? Something like that. Okay, there's a minimum here at a pretty low velocity. And I think typically it's below the velocity at which thrust required is minimum. Now as we go up in altitude, this starts to look something more like this. So the entire curve just kind of shifts. Okay? So power required is a function of altitude, as you can see by this density term, which changes with altitude. And it's a function of the design of the aircraft as well as velocity. Okay?